has fucking like 4 of them.
The hate is universal.
That's actually hilarious. Imagine someone watching them. So why do they always start with Eric?
Yeah, fuck Eric Weinstein. Hate that guy.
Apparently
Kidding.
the interview we did on what's his face, Piers Morgan against Sean Carroll was filmed. Like Eric was in one of his trained people's home.
From here?
Yeah, from PI. From PI.
I mean, I don't think Sean Carroll is much better. Like,
What? I think Sean Carroll's
Sean Carroll's a lot
he's
more
not.
respected.
He's not. Like
Yeah, he's a lot more respected.
He's not more, but he hasn't done much notable work.
Sure, fine.
Yeah,
That I can
His
agree
philosophy
with.
of physics.
But yeah, I was gonna say, like, in his podcast, when he talks about like the philosophical frameworks that other influential works have, I think that
But again, anyone who does like physics in any capacity has to be reasonably like
Philosophical.
so like smart and everything. They like
Have you
to
heard?
be like.
Have you
can't be
seen
nitpicking.
Tim Maudlin?
No.
Oh, do you know the Robinson Earhart podcast? Oh, he's good. He does like philosophy. I don't know if you're interested in that stuff.
I like philosophy of science. So it's
Yeah, so
yeah.
Tim Maudlin is philosophy of physics,
Okay, yeah.
and he talks a lot about time. But I mean,
Yeah.
just like the most clear, concise, detailed podcast you'd ever listen to about the philosophy of time.
There's this one guy, I forget his name, but he was on the Theory of Everything podcast.
What podcast is that?
Like,
Who does it?
Kurt J. Mungo. Yeah.
The-
He was a Harvard guy, philosopher of science. And he had some, I forget his name, I'll send it to you when I find it. But
The Theory of Everything?
Theory of Everything, I'm sure you've seen it.
Yeah, it sounds.
Okay, I got it working. Hopefully, for now.
His name is Jack Mungold?
Yeah.
Kurt.
That's pretty funny. Oh, I know this guy, yeah.
Yeah.
His name is Jack Mungold. That's
I forget his name, but he often has this interesting philosopher.
Yeah. Well, the only thing I watched from him, like in full, is that one video of the philosopher that just dip tap into the.
Oh, yeah.
Oh, what?
I forget what it was, but it was a debate between was it Tim Maudlin or
Yeah.
Sean Carroll?
No, Tim. It was
Tim Maudlin versus other guy. Okay, versus. So they were
starts
talking
with
on
a
the
J.
podcast. Yeah, and then the guy was like, "Oh,
Yeah.
the podcast was literally like Tim Maudlin was saying like, okay, wait,
What's
you're
this guy's
saying-
name? Tim?
All right, are we
I'm
ready?
Tim
Okay.
Maudlin.
All right,
Maudlin
shut up. We're
outside.
going. Shut up. Shut the fuck up. Okay. So, recording started. So welcome back to the talk, the second talk of this term's seminar series. I started last week with Clifford Algebras 1. On this talk, we introduced Clifford algebra in terms of a quadratic form on a vector space. We defined it as the quotient of the full tensor power, or for the full tensor algebra of V modulo an ideal, which essentially just says that V squared is equal to minus QV times the unit in our algebra for all V in our vector space V. And we particularly want to think about non-degenerate quadratic forms, or equivalently, they're bilinear forms that are associated to them. We use the same notation for that. Non-degeneracy meaning that the only thing that pairs to 0 with everything else is 0. So just make sure that when you write down the matrix representing your form, it has a non-zero determinant, basically. Okay, so in this talk, we're going to specify in particular to Clifford algebras over the real line. Last time we talked about a general K, where K was usually R or C, but today we're just not going to really think about C very much. We're going to restrict specifically to the real case. I also mentioned last time that for any real vector space and any non-degenerate bilinear form, or quadratic form, you can always choose a basis so that it takes this form. It's you sum up the squares of the first R coordinates, and then you subtract the squares of the last S coordinates. And so this defines our Clifford algebra with index R plus S. Take the real vector space of dimension R plus S and this quadratic form, and then we form the Clifford algebra out of that. Then we had some 3 specific nicer algebras that we're not actually going to talk about today. They'll come back into play next week, or next time when we talk about representation theory. We had a subgroup, which was just given by products of vectors, where each vector has a non-zero value under this quadratic form. So having a non-zero value under the quadratic form meant that our magical homomorphism, the adjoint representation, when we apply the adjoint representation to our V with a non-zero Q value, the resulting operator takes a w, a vector w, to the reflection of w through the hyperplane orthogonal to v. So in particular, the adjoint action for any vector preserves our underlying vector space v, and in fact it acts through orthogonal transformations. So if we take the product of elements in v, because the adjoint action is a homomorphism, this gives us a group homomorphism from this group to the orthogonal group, and its kernel is just the non-zero scalars. Then we have some special subgroups of this P, where the vectors in our product have not just non-zero values of Q, but they're actually plus or minus 1. This kind of normalizes everything so that the kernel is now just plus or minus 1. Still get a surjective onto OR, or onto the orthogonal group from our pin group, but if we restrict even further to spin, which was where the products of vectors, you have even vectors, and so the determinant is then going to be plus 1, because it's a product of an even number of reflections. Kernel is still going to be plus or minus 1. So we got this double cover of our group SO that we called spin. So our adjoint representation I just wrote down so you remember. You can almost conjugate, but that doesn't quite work. You get a sign here, so you have to introduce this alpha, which I should recall what this is. Alpha was our grading involution that sends CLVQ to CLVQ. So on an individual vector, it maps it to minus the vector. And so on a product of vectors, you just apply minus to each individual entry, and it comes out as a minus 1 to the number of entries. So alpha fixes vectors that are just written in terms of linear combinations of an even number of vectors. And if you have a linear combination of an odd number of vectors, it'll give you minus. But yes, so this alpha is our grading operator. Comes into play a lot. So today we're going to keep on trucking. I'm going to start by talking about the volume element, which is a very fun little thing. So suppose you have an oriented vector space. So if you took my class seminar, if you saw my seminar lectures last term, you would have seen an orientation for a vector space. It's just an ordered basis modulo the action of the special linear group. So if we start with an oriented vector space and a non-degenerate Q bilinear form, so if we choose a normalized Q basis, meaning that they are orthogonal with respect to Q, and they have, basically this form with respect to Q, which is oriented, so a normalized oriented basis, meaning it's in the same equivalence class as our chosen orientation, then we define the volume element to be the product of all of the elements in our oriented basis. And it's a fact that I won't go into, that this is independent of the oriented basis we chose. So one way of seeing this is noticing that this is in the subgroup generated by lambda NV. So remember we had linear embeddings from all of our exterior algebras into our Clifford algebra. So this volume element lives in the embedding of this, and this thing is invariant under the action of SOV. It's maybe not a great argument. Anyway, I didn't want to get into the details of that, I just wanted to mention it. That's one way of seeing it. What's more important is algebraically, how does our volume element behave? So if you square the volume element, you actually do get a scalar, and you get -1 to some interesting power. So you get down in the degree 0 elements. And if you take any vector, it anti-commutes with the volume element. So it's really helpful actually in a lot of cases that we're going to see pretty soon to have something that actually anti-commutes with everything that you care about. So it follows from the second one that if n is odd, that means that omega commutes with all vectors, and so it commutes with all products of vectors, and so it's actually a central element in this algebra. On the other hand, if it's even, and is even, we don't get it central, but we can move it past an arbitrary element of the Clifford algebra at the expense of introducing the grading operator. So this is for anything in CLVQ. Okay, so just a quick proof, both of these are just easy calculations. So first of all, write down what is omega squared. It's E1 up to En, and then E1 up to En again. Since this is a Q basis means that they actually anti-commute. So maybe I write this over here. So, yeah. How do I say this? I'll just say 0 for I not equal to j. And then they commute if I is equal to j because it's just itself squared. So, in other words, in order to take this half, e1 up to en, and rearrange them to make en minus e1, you have to count how many transpositions you make. If you add them all up, you get the sum of numbers from 1 up to n minus 1. That's n times n minus 1 over 2. And another way of writing that is just n choose 2. So in order to arrange this so that you get them all in the reverse order, you get this sign. Once they're all in this reverse order, they start to pair up. So en, so en squared, by definition, this becomes negative q en. And that's a scalar, so you can move it out, then you get en minus 1. That squared becomes negative q en minus 1. You move that out, etc., until you just get the product of negative q of ei for each I. But q of ei, remember our q over there, the first r give you a plus sign, the last s give you a minus sign. So when you flip the parity, it's the first r that give you an additional minus 1. So this is why you get this minus 1 out of that big product. Just a combinatorial thing, it's not that hard to see. It's even easier to see why the second one is true. You just have to check it on a basis. So if you take ei times omega, well, it anti-commutes with each of the ei's that's not equal to I, or each of the ej's that's not equal to I. But when it hits ei, you can just move it past itself for free. So you get one fewer sign than there are elements in this product. So then if you take an arbitrary v, write it in terms of a basis, each of these ei's anti-commutes with omega, and so omega moves past and collects the sign of n minus 1. Okay. So it's just supposed to be just a fun little calculation. So we'll need this in a little bit. So I'm going to move into what I promised. We're going to talk about the structural results for Clifford algebras. The idea is you'd like to just choose an R and S and write down a convenient description for what is this algebra in terms of simpler algebras that we already know. And so I'm going to talk about some theorems for decomposing these algebras. Okay, so suppose we have the following circumstance. Okay. So suppose V splits as a direct sum, and our quadratic form also splits as a direct sum of some q1 plus q2, where qi is non-degenerate. Might not even be non-degenerate. Don't even worry about that. So suppose that we have our situation splitting up as a direct sum. So we'd like to say that our Clifford algebra, this thing that is a direct sum, should somehow decompose into the pieces. This is what we'd like. And we don't know really what the operation should be that goes in between. So just by counting dimensions, so the dimension of this side is equal to 2 to the dimension of v. Dimension of this side is 2 to the dimension of v1. And then, well, we don't know. And then this thing is 2 to the dimension of v2. But this is equal to the product of those two. So you expect on the right-hand side, whatever this operation is, should be multiplying the dimensions of these two vector spaces. So we think that question mark should be tensor product. Okay, so let's try to get an isomorphism between this Clifford algebra and just the tensor product of these two. So I'm going to make a note about the universal property. I should have maybe recalled that earlier. It would have been more organized. So this is our main tool for producing maps coming out of the Clifford algebra. So if f is a linear function vector space to an associative algebra. With the property that for every v, the square of f gives us what we need it to be in the ideal that defines the Clifford algebra over v. So its image in A, if you square it, it should be the quadratic form applied to v with our minus sign as always, make that more prominent, times the unit of A. So this is kind of inconvenient to check. This is something you have to check on every v. It would be more convenient if you had something you could check on a basis. But since this is a quadratic thing and that's a quadratic thing, it's not enough to just check this condition on a basis. So yeah, I should finish the statement first. If you have such a linear map with this property, then we get an algebra map. It extends uniquely to an algebra map like this. Algebra map. So here's an equivalent condition. If you consider the polarization instead QV comma W, you have to have that f of v times f of w plus f of w times f of v should be equal to minus 2 times qvw. So you can see if you plug in w for v, you recover this. And this is times the unit of A. And it's not as easy to see, but the other way around is also true. By writing q of v plus w and expanding everything out. So in this case, now we have something on the right that's bilinear, something on the left that's bilinear. It suffices to check this condition on the basis. ID, and in particular, if E1, ER, i.e. f of I, oh, and we can write this, right, this is also has a better name, this is called the anti-commutator, right? So this we use a different notation, squiggle brackets. This is how we define the anti-commutator in any associative algebra. And so we need to check for all ij that the anti-commutator of f ei with the anti-commutator of f ej is equal to the polarization ei ej. So if ei to e r plus s is a normalized Q basis, and then the Q ei ej just becomes a plus or minus delta ij, depending on if I is less than or equal to r, or if it's bigger. Yeah. So this is the condition that we're going to check in order to verify that our maps actually are maps of algebras. Okay. So let's go back to our problem that we're trying to solve to see what we can get. Okay. Let's see what goes wrong. Okay. So let's take r to the r plus s with normalized Q basis. I think I start to use colors now. So I want to use green to say this is the basis that Q is positive on. So E1 up to ER. And then red for the basis that Q is negative on. So ER plus 1 up to ER plus S. and now try to make a map from R to the R plus S to the Clifford algebra on R to the R with the positive definite quadratic form, which is I, tensored with CLRS with the negative definite quadratic form minus I. Is this what I wanted to do? I think I'm jumping the gun here. Yeah, I don't need these to be special colored yet. Yeah. So let's let E1 up to, say, En1 basis for E1, and say epsilon 1 up to epsilon N2 basis for 2. Right, and so now we're trying to get a linear map from V, which is the sum of V1 and V2, so the basis is just the concatenation of the two of them. That's also a Q basis. So I'm taking Q bases. So we want to take this basis, make a linear map into this tensor product. So what we want to do, take one of our E's. Why don't we just take it to EI tensor the unit over here, and epsilon j to the unit tensor epsilon j. So this is our try. So a lot of the time when you're trying to, decompose something into a tensor product of two things, it makes sense to just do, whatever's on the left tensor 1, and then everything that's supposed to be on the right goes to one tensor the thing on the right. And our commutativity relation holds for EI and EJ separately. Sorry. So our condition holds for EI and epsilon j bases separately. Just because, if you take the anti-commutator of, say, the image, so let's call this function f. So we want to evaluate f of EI with f of EJ. And this is just equal to EI, EJ, tensor 1 plus, tensor 1 plus EJ, EI, tensor 1. And then by bilinearity, we just get EI, EJ plus EJ, EI, tensor 1. And then this is negative 2 delta ij, a scalar, is 1 tensor 1, which is the unit of this algebra. So that works. The analogous thing for the epsilon I also holds. You just do the calculation in the other part. But what if you try to do the commutation relation between these two vectors, the bases rather? So let's do an EI and an epsilon j. So this is going to be an EI tensor epsilon j. Well, I'll write it out even more full so that you can see exactly what I'm doing here. So by definition, this is EI tensor 1 times 1 tensor epsilon j plus 1 tensor epsilon j times EI tensor 1. But both of these products, they just give us the same thing. Plus EI tensor epsilon j. So this is equal to 2 times this tensor product. But what we needed it to be was 0. Okay, so the naive map that we tried to construct doesn't actually produce a map from the Clifford algebra on the left-hand side to this tensor product on Clifford algebras on the right-hand side. So I'm going to suggest 2 ways of fixing this. So we don't get satisfied condition. I'm just going to be calling it informally. I'll call it condition from now until forever because I don't have a name for it. So fixes, what can we do? First fix I'll talk about is fix the tensor product. problem is that we're multiplying these vectors together wrong. Maybe this product shouldn't be equal to this product. Maybe there's a different product operation that we can put on this vector space that actually gives us the result that we want here. So fix a tensor product to get what we expect. And the other fix, which is much more complicated, is to expect something different. So maybe it decomposes into a regular tensor product, which is not exactly in this way. So the first one's going to be much easier to describe.
These are two independent fixes, right?
Yeah, so they'll produce something else. So for the first one, I'm going to define a different tensor product operation for algebras and say that this actually does decompose the way that you expect with that tensor operation.
Yeah.
The other one is going to be, well, if we still use the undecorated tensor product, we'll get a different result that just doesn't really look as nice. So there's two different results that are both true.
So there are two different results. Oh, okay. And then
Yeah.
which one would be?
We'll see. We'll get there.
Okay.
Yeah, we'll get there. So one thing at a time. So it doesn't induce an algebra map. Oh, make good progress. Okay, so here is the first fix is the Z2 graded tensor product. So our Clifford algebras, like I said, I just erased the grading operator pretty recently. The Clifford algebras have the extra structure of being a graded algebra. So there's the even parts and there's the odd parts. So if we have two, say if A and B are two Z2 graded algebras, define. So I'm going to use a tensor with a hat on it, the Z2 graded tensor product, to have the same underlying vector space. So just the tensor product of their vector spaces. So I think I'll write it like a vec A tensor vec B, just to emphasize that we're only focusing on the vector space. It's not a great notation, don't worry. But the product is given by this. So if we take, say, an A1 tensor B1, I'll put little hats on it for now, and then I'll forget about the hats later, times A2 tensor hat B2. Well, all you do is you take the normal component-wise multiplication and you introduce a Koszul rule. You have to move the B1 past an A1, so you have to multiply by -1 to the degrees of both of these. So to the degree of B1 times the degree of A2, A1, A2, tensor, B1, B2. Where this only makes sense, of course, A2 and B1 are homogeneous. So being Z2 graded algebras means that A and B have a decomposition into A0, A1, B0, B1 as a direct sum of the even and odd parts. So to define this on an arbitrary element, you write it as a sum of even and odd parts, and then apply the product rule to only the homogeneous elements. So now my claim is that if we use this tensor product, then that theorem is true. So Clifford algebra for a direct sum of quadratic spaces is isomorphic to the two quadratic spaces Clifford algebras Z2 graded tensor product. so the proof, the only thing that went wrong over here was when we had things like EI tensor 1 and 1 tensor EJ. If we just have the EIs and EJs left on their own, what am I trying to say? Yeah, you'll still get the anti-commute. So I'm just going to check to make sure that this works on two different ones. So EI epsilon j. Let's make sure that this works now. So this was going to be equal to what? So this is EI tensor 1, 1 tensor epsilon j, plus 1 tensor epsilon j, EI tensor 1. Okay, so now let's do the causal rule here. I'll put the little hats on it to remind us that we have a different product operation. 1 is even, so there's no sign. This is just EI tensor epsilon j. EI and epsilon j both have degree 1 as their vectors. So we get a minus EI tensor epsilon j. And so we do get 0 like we want. So the stuff that's in the basis, so the stuff in the EI basis and the stuff in the epsilon j basis, their images now anti-commute in the image algebra, which is what we needed to happen to be compatible with the algebra structure in the domain algebra. So, and the thing that made it work was precisely introducing a sign when you have to, move two odd dimensional elements past each other. So that's cool. That ended up being very easy, and we get a very immediate consequence for our real Clifford algebras. I'll leave that there. Corollary. So so CL R S. Remember what this was exactly. This is CL R plus S. And our quadratic form was already diagonalized. Right? So this already splits up as a direct sum of a bunch of one-dimensional spaces, and on each space you either have the positive definite product or the negative definite product. And so this splits up very easily. CLR1 plus, and you have tensor power to the R. And then CLR1 negative 1 out of the S. And just recall, this was the complex numbers. And this was, I believe it was this. So in terms of our Z2 graded tensor product, we have a really, really easy formula. This is what the spaces look like. Problem is that, well, it's annoying to compute things like this. What is this in general? Okay, well, it's this many ungraded tensor products, this graded tensor product. What is the graded tensor product in terms of simpler things that we already understand? Is it just adding, are we just obfuscating the structure in notation, basically? Just for an exercise, this is a fun exercise that confirms something we saw last time, I'm pretty sure. Take the complex numbers with the complex conjugation as your graded algebra, and take the Z2 graded tensor product with the quaternions, also with a conjugation, and what you're going to get is, another copy of C, and what you get is the quaternions. So there's a fun exercise just to play around with this thing. So this is not as practical as the decomposition in terms of the regular tensor product. But it's important to bear in mind because I think it comes back later when we're talking about representation theory. Okay, so how much do I want to motivate this with words?
I have a question.
Yes.
So is the problem if R is bigger than 0, is the problem if I do H, the quaternions you're finding tensor product with C, is that complicated to compute as well? Like if I take R equals to 3 and I try to compute like 3 times this tensor product, is that going to be bad or?
Yeah, it's just kind of like it's not going to be immediately clear what you've produced.
Okay.
I guess like you'll be able to sit down and you'll work out, okay, maybe these are generators, maybe this is the product rule, and then you can probably piece together like what you've managed to construct. But it might end up being a little bit ad hoc depending on like what the case is. Like if you wanted to just like start increasing R and see what you get when you tensor on more and more copies of C, yeah, it starts to become a little bit less clear, I guess, as R increases. I haven't actually tried to do that, I'll be honest.
I have another question.
Yeah.
I missed the first part, so maybe you explain it there. But this tensor product in the underlying vector space, it's tensor product over R?
Yes, yeah. So everything I'm talking about, unless otherwise specified, all of these are real algebras.
Okay.
And so as vector spaces, you're tensoring the underlying real vector spaces. Yeah. Yeah, I meant to not delete this. That's okay. This is the thing that we want to remember right there.
Can I have one more question? Sorry.
Yeah.
And I guess it's not clear to me from this. I don't play with these things, so I don't really know. But it's not really clear to me from this multiplication rule. Is like this tensor, like this Z2 graded tensor product. Is it also like satisfy all the usual properties of a tensor product? Like it has some universal property like associativity or stuff like that up to isomorphism.
That's a good question. Yeah, I believe associativity and commutativity up to isomorphism shouldn't be too bad. Maybe it's commutative up to anti-isomorphism, actually. For universal property, I'm not sure. Like you're thinking, okay, if you have a pair of bilinear maps, or sorry, if you have like a bilinear map out of the Cartesian product, do you get a uniquely induced one out of the graded tensor product, for example?
Yeah.
Yeah, I didn't think about that. It's a good question, though. Yeah, I wonder.
Wait.
Yeah.
What the heck is anti-isomorphism?
So you can talk about like an anti-homomorphism. So G, H groups, for example. So phi, anti-homomorphism means, yeah, so the phi reverses the order.
Oh yeah, okay.
So I didn't manage to talk about the, transpose, for example. Transpose for going from, n by m to m by n.
Yeah.
That is an anti.
Yeah.
Anti thing. Yeah. Okay. So let's do try 2. Change expectations. It's probably not just going to decompose in this very clean, easy way that we'd like it to. As I was saying, I have to see if I want to actually try to motivate this by working towards the solution or just state what the solution is and then explain why it works. I can't just like hem and haw because that also wastes time. Okay, yeah, let's try explaining it like this. So what was the problem over here? Was that, right, these two didn't anti-commute. In fact, they commute because you're doing operations in different slots. So the fix that we're going to try to propose is instead of putting a 1 here, what if you put something that anti-commutes with all of these guys? And so in particular, before you showed up, we were talking about volume elements. And the volume element for an even dimensional vector space always anti-commutes with each of the basis vectors. In fact, any vector from that vector space. And so maybe what we can do is say, well, if there's only evenly many of the epsilons, maybe we could just multiply them together, put their product here as the volume element, and then see if that map that we define is going to give us an actual algebra map from V to the actual tensor product of something and something that we'll have to figure out. So that's the word motivation. Okay, so let's say, for example, say that V2 is the span of only two things. Let's say we have an epsilon 1 and an epsilon 2. And then try going from R to the n plus 2, yes, Rn plus 2 to CL something, tensor, say CL also something. We don't know yet what those things are going to be. So we'll take the epsilon i's to one tensor epsilon I, or j, and we'll take the EI now to EI tensor, the volume element, epsilon 1, epsilon 2. So I'll just save myself a little bit of time. I'll call this omega. Okay. So if we try this, well, it works. I'm just going to say claim if I'll just write down what the answer is. So this little thing to change what we expect, this actually does give us an algebra isomorphism from the Clifford algebra of Rn plus 2, the negative definite by linear form, with CLn0 tensored with CL02. So it's a little bit weird, so we have to change our expectations that, so the two-dimensional thing that we're tensoring with, whatever definiteness that is, that's the definiteness that we end up with, and it flips the definiteness of what we started with. And so the reason that this works, well, this is an exercise in just checking this relation. So it's clear that this relation is going to hold on the epsilon j's because we haven't done anything weird to it. And I think it's probably worth it to actually go through the calculation to check that the other two work, so you get some idea for how these arguments go. Because there are a lot of like unverified details in the book and exercises that I was able to work out, and they all amount to just writing down a map in a clever way and then verifying that this relation works. Okay. So let's give this map a name. Oh, I wish I hadn't written it all the way over here, man. So let's say that this is F.
Going back to where we had.
I hope I wrote that in the right spot. So let's take an FEI with an F epsilon j. And what do we get? So we said this was EI tensor omega, and then 1 tensor epsilon j plus 1 tensor epsilon j times EI tensor omega. Remember, there's no weird multiplication now. Now this is just the plain tensor product. So this is going to be EI tensor omega epsilon j. And when we do this product, we're going to get another EI. So we can just write this immediately like EJ times omega. But, like we said, omega anti-commutes with epsilon j, and so this whole thing is 0. And that's what we wanted. We wanted that the image of these two anti-commuting elements should still anti-commute. So like I said, we haven't done anything weird with the epsilon j's, so we need to also verify this condition for the EI's. So let's take an EI and an EI, or an EJ, and verify this. So we get, just going to write it all out. Nothing weird happening. So we get an EI EJ plus EJ EI tensored with omega squared. Okay, so omega squared, in this case, right, it's -1 to the 2, choose 2. And R is 0 in this case. So that's 1, that's odd. Omega squared is -1. So we're going to get, so this the anti-commutation relations, or the commutation relations kick in. This is 2Q EI EJ, where Q is, sorry, I have to be careful now. This is the Q1, right? So this is the quadratic form on the V1, and then we're tensoring with -1. So this is equal to 2 Q1 EI EJ, and, well, we want to have a negative here. We'd like to have a negative here. Our quadratic form on our subspace V1 has its opinion about what its value at EI EJ should be. We want the anti-commutator over here to agree with the quadratic form in our domain. This explains why we have to have the sign flip. Whatever the quadratic form is in our domain, it has to have the opposite sign of whatever it is on our subspace V1. So this has got to be -2 Q EI EJ times the unit. And this is times the unit. Okay. So that's a little bit maybe hard to see. It's one of those things, like there's a lot of things in this story where you really don't understand it until you sit down and do the calculations yourself in like a quiet room with a nice fresh piece of paper. It's hard to just hear it from somebody else.
Sorry, could you repeat that argument? So why is the negative?
Yeah, so let's maybe try to be more clear about what our forms are. So we have Q1
Oh, it gets different.
is defined on the first. So this is defined on the first n things. So if this is VI, EI, what did I write? I think I wrote, that's going to be plus. So this is the sum of I of VI squared. And Q, which is going to be the sum of n of VI, EI, and then also plus W1 epsilon 1 W2 epsilon 2 is equal to the sum over I minus VI squared minus W1 squared minus W2 squared. So the quadratic forms that are defined for these two algebras, I said that the one on the left is negative definite. Oh, it's time to feed the cats. And the one over here is positive definite. And so when the Q1 is the thing that gives you the sum of the squares, the norm squared, and the Q gives you the negative of norm squared. And so if you look at, so when you do this calculation, so this algebra that's happening here is on our Clifford algebra for Q1. And so the commutation relation which is happening there is saying that this is -2 times the value of Q1, because that's what's going on in that algebra. And then when we compare Q1 to our Q on our E basis elements, we find that they are the negative of one another.
Okay. Yeah, no, I just didn't. I thought they were the same Q, but no, it's a different one. It's
Yeah,
the
yeah,
Q1
yeah.
and the QQ.
Yeah, yeah.
Yeah, okay.
I forgot to make that like clearly distinguished, but yeah. So that's a good question. This is on. It's 2, and this is on. Okay. So, yes. So that justifies why we have this weirdness happening, why you have the sign flip going from this algebra to this algebra. And it really comes down to the fact that what we're introducing from this algebra is a volume form, a two-dimensional volume form. By introducing that into our actual function, we get an isomorphism of Clifford algebras. I just showed that it actually gives us an algebra morphism. I didn't say it's an isomorphism. This comes down to the fact that find an additive basis for this and show that this is surjective onto that additive basis. And so it's surjective, and you show also that these elements are all linearly independent. So you also get an injection. The tricky part is actually constructing the algebra homomorphism. And that's done by this. So similarly, you can go on the other side. I'll just collect this together as one theorem. So this is the main structure result for Clifford algebras, real Clifford algebras. I'll just write this, really important. So like I just said, we have an isomorphism. Well, analogously, I'll do it like this because we're used to usually, well, I'm used to reading things from the left first. So I'm going to start with this case. But the one, it's entirely analogous to the one that I just argued, which is this. And there's a third one, which is similar, which I'm not sure where I wrote down. Here it is. This one's really interesting, actually. So you can actually increase both of the indices by 1 by tensoring on this. So we've seen the first two. How does the third one work? I'll just say first two is check. Yeah, this time I'll use colors. Okay, so consider the basis. E1 up to ER, and then an epsilon. And then we get a B1 up to BS and a beta. And this is for R plus S plus 2. So this is a Q basis for the QR plus 1, S plus 1 form. So this guy says that these things have positive value and these things have negative value. Okay, and so what we want to do is get a linear map from this vector space to this algebra where the relation, the condition is satisfied. So let's define R plus S plus 2 to this algebra. We're going to define a linear map on a basis. And what we're going to do is send EI to, how does this work? Let me just look up this real quick. Sure. EI tensor epsilon beta. And BEJ goes to EJ with an epsilon beta. And then epsilon and beta, you don't really do anything. So epsilon goes to what? 1 tensor epsilon. Beta goes to 1 tensor beta. Where the idea is that these green ERs become the basis corresponding to this R, the red BS are this S. This epsilon gives you the first one, and this beta gives you the second one. So epsilon and beta are considered the two additive basis vectors for R2 with respect to the indefinite bilinear form there. So it makes sense to send epsilon to 1 tensor epsilon, beta to 1 tensor beta. So the epsilon and beta go on the right-hand side. They get shoved into there. The E's and B's all go into there. And yeah. Interesting. So now this is a different case from where we had before. We had our omega squared 2 minus 1 precisely because these two had the same sign. Here they have different sign. So now the omega actually does square to plus 1. And when you go and you check all of the commutation relations, everything goes through without a hitch. So I'm not going to do it again because I feel like you've seen how those proofs work. So I can start to assign them as exercises now.
I have a question.
Yeah.
For the first two, I understand why you need a different proof. But for the last one, if, assuming that you have commutativity up to isomorphism and associativity up to isomorphism of the tensor product, can you not just use like this thing to get the last one? Like this corollary here? Because then you can just start moving stuff around, regrouping, and you get that last decomposition. Or am I missing something here?
You might be able to. So you mean like peel off?
Yeah, decompose them into like CLR1s with plus and minus, move them around, and then just regroup them.
Yeah, I think if you did that, you'd be left with a hat here. So you would have to maybe verify that those two algebras are the same.
Oh, I see. Okay, so this is without a hat. This is, okay, now I'm confused.
Yeah, exactly. So this is a non-hat tensor product.
So this is just tensor product as vector spaces?
Yeah. So we had to try extra hard to get a result to work out. Well, tensor product of real algebras.
Oh, real algebras. Okay,
Yeah, yeah.
Okay, I see.
So this was the tensor product where, yeah, you had to be careful when to introduce a sign when you move things past each other. But we're just taking now, we've managed to work a little bit harder to get a similar result for the ungraded tensor product. So you don't have to worry about Kozuo rules anymore. This was, it turns out this is kind of just for interest as far as this talk is concerned. We're not going to think about the graded tensor product anymore. I just wanted to show that this is one possible solution to the problem we ran into earlier. And another possible solution is just sort of try something different and come up with a result that you weren't really expecting to find.
Okay, so if I start from this one and I just forget about the grading, I don't get this other tensor product. Right? If I start from the one where you tensor product hack and I forget the grading, I don't get this. Because this is
Like it's the same vector space. That's the one thing. So the additive structure on these algebras is exactly the same. The only difference is they have a different product on them.
Okay, I see. So you did okay.
The multiplication rule is different. Okay. Question. So this is the theorem. Yeah, so this is the main structure result. This is what allows us to actually start writing down answers for what these algebras are. So.
Can you also raise the height of the demonstration, just to make sure?
Whoops, yeah. That was for demonstration purposes. Entertainment purposes only. Okay. So you can see how these are going to start to let us inductively compute what these are. And you sort of have to bounce back and forth between positive definite and negative definite in order to get those results. So I think what I'm going to start doing is just write out the big table, and then we can just start filling it in as we start to understand more and more about how the structure theorem is working and what it's telling us. So you've probably all seen a table that looks like this before. Right, a really big. This is my R direction. This is my S direction. So this is a table. This is going to be a bunch of models of CLRS based on this structure result. We're going to iteratively produce all of these values. Specifically, I'm going to want to go up to 8. I'm really bad at this, subdividing into 9. It's not my forte. Pretty good, actually. 8 over there. 4, 5, 6. I think that's pretty good. 1, 2, 3. Okay. So big table. We know for sure CL00, the zero-dimensional vector space, we just get a copy of R. Okay. So the idea, the way that we're going to use this theorem is, say you want to know this one. Say you want to know that one. So what you have to do is go down to 5 on this side. So once you know what this is, you take this, tensor it with that, and then you'll get this. So you can see that as long as you're going, one at a time, you can go farther and farther out on the two axes. And then anything that's in the interior, you can use this result to gradually peel away copies of this algebra until you land back on an axis somewhere. So as soon as we know what the two axes are, then we can just fill in the rest automatically. So we're going to need to start with some small values to get the ball rolling. So let's do low degree examples. Wow. We saw some of these last time too. So CL00, like I said, this is just the base field R. There's nothing going on there. CL10, we saw that this was the complex numbers. And that CL01 was just the direct sum of two copies of R as an algebra. So the multiplication is coordinate-wise. We also saw that CL20 was the quaternions. And it happens to be the case that CL11 and CL02 are actually two-dimensional. What am I trying to say? So if I have a field K, for example, and I put a number here, this is n by n matrices over K. So 2 by 2 matrices give us these algebras. So for a proof, we've seen these already. Well, we haven't seen this one, sure. So CL01 to R plus R. You only have one vector here, or one basis element here, and its square is +1. And so it turns out that sending this to 1 minus 1 is the desired isomorphism. One isomorphism between those two. And I'll do one of these two. Which one is that? Squares to 1, squares to -1. Okay, yeah, so CL11 go into 2 by 2 real matrices. So you have two basis vectors now. There's E1 and E2. So E1 squares to -1, E2 squares to +1. And we can send E1 to 0, 1, -1, 0. E2 goes to 1, 0, 0, -1. So this is also going to be a valid isomorphism between those two algebras. And you can go and play around and figure out what is going to be the algebra isomorphism for that as well. Just wanted to show that it's not super hard to establish these results. It's just a little bit of playing around. So we can start to fill in this table some more. So this is a C. This is an R plus R. This is an H. This is an R2. This is an R2. And like I said about using this one.
You're doing the other way around, are you? Like RMS or the R.
Yeah, I did this backwards. Yeah. It's not what I wrote on my page, so yeah, I should have looked down.
Or you would just switch like RNS, I guess.
No, this is the way that the table is presented in the book. I don't want to give like confusing. I don't want to conflict stuff. Okay, so yeah, like I said, you can just tensor with CL11 to get the diagonals. But okay, now we have a lot of things to think about because we have H's flying around and C's flying around and matrix algebras flying around, and we have to tensor these all together. So we're going to need to have a result that tells us what we're going to get when we actually do these tensor products in order to describe these algebras as simply as possible. So let's have a good old-fashioned algebra lemma. really good one. Love some of these groups. So eating our vegetables here. So we take n by n real matrices. We tensor over the real numbers, n by m matrices. And this is called the Kronecker product. We've seen these in our quantum information courses. Tensor product of two matrices gives you a matrix whose dimensions multiply. So that's going to come in handy. For example, now we can say that the 2 element is going to be R2 squared, so this is R4. 3 is going to be R8. This is going to be R16, etc. So you're going to get powers of 2 on this diagonal. We're going to end up with R to the 256 over there up in that corner. So that's nice, that helps. If we take n by n matrices and tensor in our favorite field, we just get n by n matrices over that field. Or does it even have to be a field? This has to be a real algebra. C or H in this case. That doesn't really need a proof. This one's interesting. If you take the complex numbers, tensored with itself over the real numbers, you actually just get the direct sum. 2 times 2 equals 2 plus 2, so that's great. If you take the complex numbers, tensored over the reals with the quaternions, you get 2 by 2 complex matrices. There's no intuitive reason to see that off the top of your head why that should be true. And finally, if you take quaternions tensored with the quaternions, you get 4 by 4 real matrices. Okay, so we're going to use these to help us fill in the table. I still have a bunch of time, so I'm going to say why the interesting ones are true. So let's start with 3. This one's pretty easy. Let's go from the direct sum to the tensor product. Well, let's go the other way around. So C tensor C to C plus C. I'm telling you, you can just define it on this additive basis and it works. 1, 1 goes to pair 1, 1. This is the multiplicative unit here. This is the multiplicative unit here. I tensor 1 goes to, well, it has to go to something that squares to -1. -1 over here is -1, -1. So I is something that squares to that. This one also has to square to -1. And we can take I minus I. And then I, this one squares to +1. So this ends up going actually to -1, 1 minus 1. So as you can define that on the basis. That one's pretty easy. 4 and 5 are really interesting. They're not hard. They're really easy, but they're really interesting as well. Okay. So let's consider C tensor H, and we're tensoring over the real numbers. Okay. So if we take a complex number and a quaternion, a bilinear thing that we can do, so what are we trying to spit out? 2 by 2 complex matrices. Well, that's great. Well, we consider H as a 2-dimensional complex vector space. Since the complex numbers are sitting inside of H, there's a scalar action naturally of C on H, and it gives you a 2-dimensional vector space. And you can use this action here to give us a map from H back to itself. I'm going to call phi zq, which takes an x in H, and it sandwiches it between the z and the q bar. So this is bilinear in z and q, and so this gives us a map on the tensor product. Notice that this function of x is actually z or c linear. If you had a complex number scaling x, you could move it past this z because that's also just a complex number. You couldn't move this past the quaternion, but you could take any complex scalar and move it past this z. So this is actually a complex linear homomorphism from H to H considered as a two-dimensional complex vector space. And so this is an isomorphism. That's something you just have to check. And CH, right, since it's a two-dimensional complex vector space, this is just C2. So that's a really weird argument. You start with a complex number, a quaternion, you produce a C linear homomorphism from H to H. That's just two-dimensional complex matrices. So now if you try to do the same thing with two quaternions, well, you might be able to guess what's going on. Right? You can still take a quaternion, sandwich it between them, but now this isn't C linear anymore. If you have a complex scalar in front of the x, you cannot move it past an arbitrary quaternion. So this is only R linear. And H is a four-dimensional vector space over R. So Hom is the isomorphism. Hom R, HH is R4. So this, when I figured this out and realized why this works, this blew my mind. Maybe no one else thinks this is cool at all. But that you get a C linear homomorphism here, and so, but you only get an R linear homomorphism here because you just can't pull the complex scalar out. So doing C tensor H lets you retain this complex, fundamentally complex thing, but H tensor H is somehow inherently only real. Okay. So with all of this in mind, we can finally start to fill in this table. Yeah. Okay. So how does this work? Like I said, if you want to get this value, you have to look at this value, tensor this. Well, this is C tensor R2. We just saw that that's C2. Now, if you want this value, you're looking at H tensor R2. That's H2. Great. Want this guy, we're going to get R plus R tensor H. So we can do that. This guy is going to be R2 tensor H. We can do that as well. 5, H plus H tensor with R2. Haven't hit anything interesting yet. We'll get there soon, I think. 6, we're looking at H2 tensor R2. Okay, so H2 tensor R2, for example. This is just H tensor R2, tensor with R2 again. R2's combined together to give a 4. H comes back in, you get H4. Where are we going? That was this one. H4. C8. Or 16. Like, etc. Yeah, I'm not going to stand here filling in the entire table. I'll fill in the walls. And then getting everything in the middle, like I said, just amounts to tensoring with R2 all the way up. You just get matrix algebras and matrix algebras and matrix algebras. So now that you have the structural theorems, right, determining the values of this table are completely deterministic. It's so deterministic that ChatGPT could probably almost do it. Maybe make 3 or 4 mistakes instead of like a continual stream of mistakes. So yeah, this is the table. I can pass around this piece of paper, or rather my notebook, so that you can look at the table if you'd like. I just wanted to make sure that we actually understood how to construct this famous table that you see everywhere. And people get a good look at it. Yeah. So I'm going to pass that around. Okay. Do a brief break for questions, I guess, while I take a drink.
It's interesting that the table's not symmetric amount of the diagonals, since the S and the R amounts to like a metric signature, right?
Yeah.
It's like, for example, like if you're doing like special alternative, people say, oh, you can use like plus 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 minus metric or minus 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 plus metric in order to be the same. But the Clifford algebras, if you want to study Clifford algebras, it's different.
Yeah, what is true is that the orthogonal group of RS is the same as the orthogonal group.
Right, right.
So
So that's all they
preserving
care
one-
about, yeah.
Yeah, so you preserve one if and only if you preserve the other one. But when you actually get the algebra, like, yeah, you can see they're definitely not
Yeah.
the same. But there are some places where you do get the same. And here, for example, R16, you get the same. But all of the other ones, you have these differences. Yeah.
It still looks like there's a lot of good structure, like really nice structure here,
Mhm.
like similar patterns.
Wait, you actually wrote it up by hand.
Yeah.
I was also gonna say that physicists, when they use like the different signatures, the 1-3 versus the 3-1, they'll use like the different conventions of like whether the vector squares to minus q or whether it squares to like q itself.
Oh, yeah.
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 Wait, oh.
Yeah, that was a question from last time, like whether the plus q or minus q makes a difference. And I think,
Yeah.
yeah, it is a convention,
Mhm.
but it's still like, yeah.
Well, you just mean like the four velocity squaring, right? The plus or
No,
minus.
like the
metric.
algebra, the Clifford
Oh, you mean
algebra.
like when they study Clifford algebras?
Mhm.
Yeah, yeah, okay, okay.
Mhm. So there's two, like, yeah, like in relativity, they compute these
Yeah.
like matrices, the gamma matrices, there's like two sets,
Yeah.
one for the each, yeah.
Oh, I didn't know. Huh.
Because here on the axes, it's like those that are symmetric. So like it's 4, 8, 0. Is it always multiples of 4 that you get the same one?
Yeah.
Is there a reason? Like that's
How do I, what's the easiest way of saying this? So this is kind of leading into these periodicity theorems. So one way of seeing it,
Sorry, which row was he talking about, or which symmetry was he talking about?
so like the 0, 4 and the 4, 0, or the other way around. Yeah, 4, 0 and 0, 4 are the same. 8, 0 and 0, 8 are the same.
Sure.
So
yeah.
whenever you have a multiple of 4, you
Four.
get that thing is equal to that thing. It all comes down to this reason essentially. So
Oh, I see.
CL
even on the table you got okay.
4, 0.
Yeah,
this
right,
is
there's a lot of, like,
CL.
Like if you look at the 4, it goes the same
Yeah,
one.
yeah,
as it
yeah,
goes
yeah,
up.
yeah. There's a lot of like symmetric structure in
Well,
that.
that's just because of the.
But yeah, just the structure.
Oh, okay.
Yeah, so like if you take n is equal to 2 as well, then these are just like the same thing.
Mm.
And you can just move them around. So this is why, in particular in the case when n equals 4, you get this symmetry. Yeah. And it also keeps going. I think you can just keep going forever, like
Yeah.
inductively now. So if you have like 4k, 0 is isomorphic to what? CL 4k minus 1. So I'll do it like this.
So are we assuming this is a symmetric tensor product or?
No, this is the ungraded tensor product.
Ungraded?
Yeah, so
this
just
is
the
the
thing that
only
gives us
construction
this
we did.
result.
So here, yeah.
So CL4k. What am I typing in? 4k minus 2. Right. This is CL20, CL02, CL. No, this has to be a 0, 4k minus 2. This is CL4k minus 1, 0. And so this thing, by induction, right, we can write this. Well, if we'd like, we can switch these two around to make it a little more illustrated. And so if by induction hypothesis, this is the same as this, then you can just recombine these in this order to get this. So, in fact, we always get this symmetry in every multiple of 4, and it comes entirely down to the fact that CL04, yeah, you just have these little 2 algebras popping in when you apply the structure theorem. And this leads also into periodicity theorem that I mentioned in the abstract. So I'm going to write those down right now. The book mentions 8 periodicity theorems, but you actually get 4 periodicity. I'm not sure why they don't mention that. So it's not periodicity in the sense that you get the same thing repeating all the time, but the difference between this thing and this thing is always a tensor product with the same element. In particular, which thing? this thing. So periodicity for n greater than or equal to 0, we're going to get CLn plus 4 comma 0. Well, we get another. So if we look at differences of 4, then we don't have to switch sides. CL0 n plus 4 is CL0 n, CL0 4. And I'll remark again that these two are actually the same. It didn't matter which side I wrote it on. But when you compare these two sides, the n plus 4, the n are on the same side. Yeah. So the proof is basically just what I wrote down there. So, I'm just not gonna include it at this point. Again, I can leave it as an exercise. Okay, so there's a periodicity. This is before periodicity theorem. As a corollary, you can just apply it twice and get the periodicity theorem that they mentioned for 8 periodicity. But you could also just apply it k times and get n tensor CL or k as well. So, okay. Yeah, I guess I'm pretty much done what I was going to get to. I'm going to mention complex case and some additional observations.
I have a quick question.
Yeah.
For periodicity is as good as you can make it, only around the axes. You can never, like, you don't have any sort of periodicity on the inside? Outside of like this.
Like there is interesting structure as well that I'll get to a bit later. So there is like this periodicity. Essentially, whenever you want to increase both indices by 1, there's a fixed thing that you can tensor with that induces that isomorphism for you. So you can think about like kind of there's this 1, 1 periodicity going up all of the diagonals. But like nothing repeats, right? Just like it doesn't repeat on the axes. It's just that increasing the index by 4 amounts to just tensoring with this fixed thing, H2. And then going up this axis, you're also just tensoring with H2. There's a couple more symmetries that I'll talk about in a second as well. So, yeah. So in a complex case, so I said we're going to be talking about real stuff, but we can very briefly make some remarks about the complex case. So, like we said, every non-degenerate complex quadratic form can be normalized, i.e. a quadratic form on a complex vector space looks like, or you can choose a basis so that it takes the form of just having all 1s on the diagonal. Okay? So we're going to define CL, complex number L, n to just be the Clifford algebra of this complex vector space considered as a, right, so the general story, we can have vector spaces over any field with the identity matrix representing our quadratic form. And then the periodicity theorem says that if you take CLn and you tensor it over C, now we actually have a complex number. It's not just real algebras. Now we're talking about complex algebras. That this is, what am I saying? CL2. That this is CLn plus 2. So we have the 2 periodicity for complex Clifford algebras. Increasing your index by 2 just amounts to tensoring with this fixed thing. Do I know what that fixed thing is off the top of my head? It's the, yeah. So remark, if you take CLRS and you tensor with C, right, you're gonna make a Clifford algebra over an R plus S dimensional complex vector space. And they all have the same quadratic forms. So no matter what R and S you start with, once you complexify, they're all isomorphic. And so when I write CL2, right, this is isomorphic to CL to 0, for example, tensored with C. CL2, 0 was the quaternions. And so our periodicity algebra is, what did we say this was? How does that make sense? This is, What we know is real algebras that's isomorphic to R4, but this is a complex algebra, so I can't just say, well, it's the same as R4 because I haven't said how that's a complex algebra. So as complex. So maybe this was not a good thing to write down because it doesn't have very final result, because I didn't think through. Oops. So this is the periodicity in the complex case. And it follows from the periodicity, or from the structural result in the real case. You just have to tensor with C. So I'll end by giving a couple more really nice additional observations about the structure of this table that everybody looked at. That aren't extremely important, but we left them as exercises, and I figured out the proofs, so I want to say something about it. I'm really proud of myself. So if you take R plus S, so if R is at least 4, this is the same as subtracting 4 from R and adding 4 to S. Next, if you have a little bit of additional space, so normally you can't swap R and S, but you can swap R and S if you have a little bit of extra space. So these two very strange things are true. So I'm just going to write down these great ideas that I have. So let's let R plus S be the real span of the following basis. So we're going to have E1 up to ER minus 4, and then we're going to have sigma 1 up to sigma 4. So these are our positive guys. And then we're going to have epsilon 1 up to epsilon S. So this is in the domain. And then we're going to go R plus S to this algebra CLR minus 4 S plus 4. So the quadratic form on this algebra takes these 4 and switches them. This is why I call sigma for switch. Switches them into red ones. So the quadratic form in here and the quadratic form on here, they disagree about their values on these 4 vectors. So what I'm going to do to define my map is I'm going to take my EI's to EI's, my epsilon J's to epsilon J's, and my funny switchy ones. So I want this to change parity, and the correct thing to do turns out to be sigma k times the volume element again. So omega is once again sigma 1 to sigma 4. So this is what I figured out works. In order to switch the parity of these guys, it suffices to actually multiply by this little 4-dimensional volume element. So I'll leave it to you to go check those commutation relations. You've seen them enough today. I don't want to drag you through another one. Just
Sorry,
want to.
so I understand that there was this like repeating pattern before, especially that we showed it here. But I don't see why this wouldn't work with different values. Like why couldn't we do it with like 2 sigma, for example?
With 2 sigmas.
Or 3 or 5 or anything?
The reason is because sort of you need this omega to anti-commute with each of the sigmas, and you also need it to square to 1.
Ah, okay, okay.
So if you start changing around your parameters, you'll have like omega squaring to -1,
-1,
or
yeah,
commute with the
yeah,
wrong things.
yeah.
Yeah, exactly. So some 4 is like this really, really good dimension. because a lot of the number theory
2
just
times 2
works out.
equals 2 plus 2, that's it.
That's one reason, Okay. Right, so finally, let's figure out the last one. This one's also kind of cute. So you have a bunch of vectors of length r. Yeah. I'll just write it, it's fine. So let's take r plus s plus 1 as the span. So on one hand, you're going to have E1 up to ER is the green ones. And then you're going to have epsilon 1 up to epsilon r and an additional beta. And so this is the quadratic form you want to use in the domain. And so this is I want to say this is a QR, this is an S plus 1 basis. S. And you can also consider it as a QSR plus 1 basis, where this quadratic form just disagrees on the e's and the epsilons. So we would have that the epsilons are now positive in the other quadratic form, and now the e's are the negative ones. And the map that we define this is a kind of a funky thing. So you take beta to beta, easy enough. You take EI to EI times beta, and you take epsilon j to epsilon j times beta. So when you do this, multiplying by beta ends up having the effect of like switching the polarity of the quadratic form, so that when you evaluate the commutation relations on the right side, they give you the right values in terms of the quadratic form on the left side. So again, you can run off and verify that that gives you an actual algebra map between these two, and that it's an isomorphism. So these are some cool relations that are also some cool structure that lives inside of the table that might come in handy at some point. But I don't know, we'll see. So after this, I need to prepare about representation theory and probably talk a lot more about spin and pin again. But the point of today was to just sort of talk about this table, talk about all of these structural theorems to decompose our Clifford algebras. And now we see the punchline is that all of these Clifford algebras are nothing more than a matrix algebra over R or C or H, or a direct sum of two of those things. So when we start doing representation theory of these things, we're already off to a really good start because we just have matrix algebras over really familiar things. Okay, so that's today's talk. Okay. Questions? I feel like that one was more technical because there was a lot of little fiddly algebra. But
I feel like those guys on the internet who are like, they try and see patterns in numerology or whatever. Just like random, it's like, oh, I noticed a pattern. But like while I was looking at the chart, I swear it was like seeing patterns. I'm like, no, there's definitely more periodicity somewhere.
Yeah, there's a lot of rich structure that, yeah, I think if you sit down and stare, you'll find a lot of stuff. Sure.
The graded tensor product that we constructed before, I'm not sure if this was the same thing I've seen before, but I've seen a different thing where like you take like the even parts tensor, tensor the even parts direct sum, the odd parts tensor with the odd even with the even odd or something like that.
Yeah, I think I know what you're talking about. I can erase this now.
Even, direct sum, and then odd times or tensor or what?
Like it's a thing where like instead of tensor products you have like direct
like this is gonna happen no matter what, right? So if you have this direct sum decomposition, in terms of any direct sum decomposition,
Is that supposed to be B even or same A even?
it should be V. So just as vector spaces, when you take the tensor product, like it's gonna be like a distributive thing, right? So A, you can make A even, tensor A, B even. Yeah, I think it's like this. So if you take the graded tensor product, you get a Z2 graded algebra. This is the whole point of the product. And the even parts are this. And then the odd parts are the complementary ones. So like, yeah, the graded tensor product, this is what I meant to say. I mean, it takes two graded algebras and it spits out a third graded algebra. And this is the grading that you get. I think these are probably, well, these aren't actually a subalgebra. I think this is just a decomposition as a vector
So
space.
just, so yeah, vector space, yeah. And then the multiplication is like the one that you define.
Yeah.
The multiplication with the parity, like you
Goes over,
like
yeah.
it goes over, yeah.
Yes. Something like this.
Sorry, is there a question down here?
Yeah, I was just checking if this is the same thing, yeah.
Okay.
So we used the second fix for everything that followed afterwards,
Yeah.
right?
Do
you know what I'm gonna ask, or?
No, I don't.
Oh, I was gonna say, like, you know, what happened to the first, like, could we construct an analogous sort of, like, everything past that using the first fix, or?
I mean, yeah, you might be able to, because sort of when you're looking at this and all the dust settles, there's no tensor symbols left anymore.
Right.
So if you maybe could, you know, if you were really, really good at these graded tensor products and you could compute, like, what did we have? I don't know, like the complex numbers to the rth grade. If you could compute stuff like that easily, then, and then tensor that with the other thing,
Yeah.
you should hypothetically be able to reconstruct it, yeah.
Okay.
But I think somehow the fixed number 2 kind of gives you a lot of these weird, interesting structural results that you'd have to sort of rederive in this other context. Maybe a lot more difficult.
That was interesting because the first fix was obviously easier in terms of the fix.
Yeah.
But it makes this more complicated, and then
Yeah.
the second fix was a little bit more technical, but it makes everything else so much easier.
Yeah, it's weird. It's like, because like the normal tensor product doesn't really quite work out, it somehow makes it like more descriptive. Because
Yeah.
like what actually is true is sort of carrying a lot more content in it. Whereas this sort of is just a really formal, convenient decomposition into pieces that you understand, but you don't really necessarily understand how explicitly to reconstruct with the graded tensor product. But maybe, yeah, you might just get good at it, and then, I mean, this is just how Lawson Michelson presented it. Maybe there's an easier presentation.
Yeah, with my work with Kevin, it was all graded, and it was a pain. It
Okay.
was- yeah.
That explains why they don't do
Yeah.
that. Yeah.
I was just about to ask, like, what are applications of the graded one in terms of like?
It just came up in a lot of our work, especially with Poisson algebras, maybe? That was the content, Poisson algebras. Super stuff. It was all the super stuff.
That's what at least I could see, like this being.
Yeah.
It's all the supersymmetry stuff, yeah.
Yeah, it's kind of like more
Ghosts,
natural
anti-ghosts,
when you
all that
have
kind of jazz.
Z2 graded stuff.
So
Yeah. I don't know either. You'll learn.
If you redefine your Clifford algebra using kind of the +1 instead of the -1 sign, is the consequence like a transpose of the table? Or
I think so. I'm pretty
Yeah,
sure.
for sure.
So like when we used to get, so the H would now be the CL02 if you just changed signs.
Yeah, okay.
Yeah.
But it wouldn't matter. Yeah, it doesn't matter.
No, we
Yeah.
just swap the letters in the alphabet, etc.
Yeah. What are the
And then the eighth periodicity, like the reason people say eighth periodicity is just because like they don't care about the R16 factor.
Mhm.
Somehow the H2 is different or something, like.
Even though like you do get a periodicity isomorphism.
Yeah.
You do get this, like you don't say this in the book, but I'm pretty sure that I just simplified the proof for the A periodicity by like one step and you get this.
Yeah. Maybe
So-
there's something special about tensoring with R16.
Yeah, I mean, I know that the authors are working towards KO theory where there genuinely is 8 periodic and not 4 periodic. But if you disregard 2 torsion, then it is 4 periodic. So I think there's something subtle there that I hope to be able to figure out when I talk about Shapiro. Hopefully I
Yeah,
get
it's
to talk
bot
about that.
8. Bot periodicity is 8.
Yeah, for KO theory is 8 periodic.
But you're saying they want to make it 4?
Well, it isn't 4, but
Oh, yeah, so
your
we-
Clifford algebras have this weird 4 periodic structure.
Yeah.
But somehow, like, that doesn't survive the KO theory. It only
Oh, it only,
periodicity
okay,
does.
okay.
Yeah, do they not call that periodicity, like the A-fold periodicity, bot periodicity in the textbook, or I don't know?
I'm not sure. I think in the first few sections, I don't think they call it bot periodicity.
Oh,
they
just-
call it the periodicity
periodicity,
0 through
yeah.
quotation marks.
I've heard
But
of
this is what they like birth bot periodicity out of essentially.
Yeah,
Like,
yeah. So like through the Shapiro isomorphism,
Yeah.
it becomes
But
periodicity.
if you go to the Wikipedia of bot periodicity, they talk about like infinite limits of orthogonal groups or something. Or
Yeah,
something.
you can also phrase it as the homotopy groups of
Yeah.
O.
So
Yeah.
there's some
O.
relation there.
Yeah, the relation is between the different ways that you could represent K theory.
Okay.
So like the stable so the homotopy groups of O give you like stable vector bundles, or actually you call it, say BO. These are stable vector bundles over the I sphere. And this is also the I minus first homotopy group of the stable group O. And so the stable vector bundles, there's a stable vector bundles interpretation of K theory over, what was our assumption about that? Do they have to be compact Hausdorff? I think they have to be compact Hausdorff spaces.
Good.
But you're ultimately computing like, K star of a point. By computing K star of the sphere, suspension isomorphism says that this is K star minus I of a point. And so computing the homotopy groups of O is telling you the K theory of a point, and then the Shapiro isomorphism uses some, starts with the representation theory for Clifford algebras, and comes up with an algebra out of those, modulo some equivalence relation that also describes the K theory of a point. And so this is the why, I mean, these two approaches they give you the same thing. So when you go and see bot periodicity on Wikipedia, they're probably talking specifically about the vector bundles interpretation,
Yeah.
rather than the Clifford algebra approach.
So really, I mean, the Clifford algebra approach is still saying something about the topology of spheres. I guess, like, because if you can convert it to the kind of homotopy of the orthogonal group language.
Yeah, yeah. So I mean, the Clifford algebras also says a lot of weird stuff about like vector fields over spheres.
Yeah.
So that's something I hope that I get to say something about as well, because I never actually understood that story in its entirety. But like this was what Adams did.
Yeah.
I was gonna ask, what are your plans for after this?
You mean after?
Like next, yeah.
Well, the next talk is going to be about representation theory of Clifford algebras,
Yeah.
leading towards the Shapiro, and then I guess probably I'd want to talk about the vector field problem.
Oh, okay.
I realized the other day that my thesis was about the vector field problem, even though I tell people it's about Madsen-Tillman theory, but really it's about the vector field problem. Yeah. So that'd be good to talk about. Probably won't get to talk about the Hopf-invariant one problem.